Hi, today I'm going to walk you through our notes on types of forces and how we illustrate those types of forces that are acting on objects in something called a free body diagram. So use the information on this page to set up your journal for today's notes. You're probably going to need 2 pages, a 23 and a 23A. So our first word, which we've been talking about for the last few days, is force. A force is any kind of a push or a pull that acts on an object and affects its motion in some way. As we know, the unit for force is newtons, and that's a capital N. The symbol for force, how we show it in our equations, is a capital F. And remember again that these capital versus lowercase are really important because we're going to use the other version of them at some point. So capital N for newtons, capital F to show force in equations. And then we'll use what's called a subscript. That's the little letter or letters down at the bottom, and that is going to describe the type of force. What we saw in the last set of notes was F net, or the net force. Okay, I also used FW for the force of weight. You could also have FF for the force of friction, which is one of the forces we'll be talking about today. And remember also that force is a vector quantity. Force has direction. A lot of times the the direction is implied in the question or in the answer itself, but it is important to remember that it is a vector. And we can add forces just like we added vectors. Show the arrows, look at the length of the arrows, and see what would happen when we combine those different arrows. Then we have this thing called a free body diagram. Free body diagram just shows all of the different forces that might be acting on an object at any given time. That's going to include gravity, it would include air resistance, it would include anything that's making the object move or not move. And we show that with these force vectors, remember those arrows, and they originate at the center of the object. We're always talking about the centers of objects when we look at forces. We can represent the object in a free body diagram with a realistic picture. So if we're talking about all the forces that are acting on, say, an airplane, we can draw a picture of an airplane and show all the force vectors that are coming out of that. We can just use a dot or a box or an oval or anything that just says, here's the object, and then showing all the arrows coming out in the various directions. In the examples that I'm going to give you in today's notes, I'll be using an oval with the force vectors coming out from the center. So now we're looking at all the different types of forces. Now I can't possibly tell you all the different types of forces, so we're going to focus on 6 that are kind of most common and sort of generic. So our first one is the force of gravity, Fg. The force of gravity is caused by the acceleration of gravity. And we know that gravity always points toward the ground. And then we have this thing called a normal force, and that's kind of a weird concept, but a normal force, Fn, is just the thing that keeps objects from being pulled through surfaces. So when you're sitting on a chair, the reason why gravity doesn't just pull you right through the chair is because there's a force pushing back up on you called a normal force. A normal force is perpendicular to the contact surface. So that's a key word, contact surface. You only have a normal force when the object is in contact with something else. Now let's take a book just sitting on a table. It's not moving, it's not going up or down or side to side, it's just sitting on a table. What forces would be acting on that book? Well, we would have the force of gravity, which is pulling it down. But then we also have the normal force, perpendicular to the surface of the table, but that's what keeps the book sitting on the table instead of being pulled through the table by gravity. In your notes, I would like for you to copy just this free body diagram, just the oval with the gravity force and the normal force showing. Our next force is friction, and most of you have heard about friction or are familiar with what friction is. We show friction with FF. Friction is something that opposes the forward motion on a surface. So whatever direction the object is moving, friction is going in the opposite way. And it's going to be parallel to the contact surface. So just like a normal force, in order for friction to apply, there has to be contact between the objects. Then we have what's called an applied force, FAP. And that could be anything. It could be a push, a pull, hitting the gas pedal in your car, hitting the brake pedal in your car, anything that physically pushes or pulls an object. Okay, so like I said, a physical push or pull, either forward or backward, the direction doesn't matter in terms of whether it's an applied force or not. So let's say we have a car that's driving at constant speed. Now, those of you that drive or have ever been in a car, hopefully you know that in order to keep up a constant speed in the car, you have to keep applying your foot to the gas pedal. That's because there's friction on the wheels of the car going the opposite way, and you have to keep applying that force in order to keep the car moving. So a free body diagram for a car driving at a constant speed might look something like this, where again we have the gravity force pulling it to the ground, normal force keeping it on the ground instead of through the ground. We have our applied force, that's putting the gas pedal to move it forward, and then we have our force of friction. That's why it's going at a constant speed instead of constantly accelerating. Okay, you notice that the applied force vector and the friction force vector are equal to each other here. So all of these are pretty much equal, and yet the thing is still moving. We're going to talk about that in just a minute. Then we have a tension force, FT. Tension force is what we call a hanging force, when anything is hanging from something else. And that usually results from pulling on the end of an object like a rope or a string. It could be the strap on a bag. It could be a rubber band, anything that's hanging off of something else. So for example, let's say we have a light bulb that's hanging from the ceiling, one of those fancy ones that's a bulb on the end of a cord. In that case, we would have two forces. We'd have the force of gravity, as always, pulling down on the object, and then we'd have the tension force in the string or the cord that is hanging the light bulb. And they're equal to each other, so the light bulb is not moving, it's staying in one spot because it's being pulled equally down and up. So put this in your notes, just the free body diagram. Next one, pretty much everybody's familiar with this, even if you're not completely sure how it works, is air resistance, F, air. And air resistance results from moving through the air. Usually that is when you're falling is when we apply air resistance most often. So let's say we have this skydiver that's falling at terminal velocity. Terminal velocity means he's not speeding up anymore. He's still going toward the ground. He's obviously not just stopped in midair. But terminal velocity means that you're not accelerating anymore. You're falling at a constant speed through the air. And the free body diagram would look like this. So he's being pulled down by the force of gravity, but then he's being kind of pushed up by the force of air resistance. And because he's falling at terminal velocity, we know that those two are equal. If he was still speeding up, if he was accelerating as he got closer and closer to the ground still, then this air resistance force would be a little bit shorter. There wouldn't be quite as much air resistance as there is gravity pulling him down. Now remember from your last set of notes the net force. Net force is the vector sum of all of the forces that are acting on an object. So you have to take into consideration all of the directions, all of the magnitudes of the forces that are acting on the object to figure out what the net force is. So we show that with F net. And when you're adding force vectors, there's a couple things to remember. Going up and to the right are considered positive directions. Going down and to the left are considered negative directions. Now, in your Newton's first law assignments, in the videos, they talked a little bit about balanced versus unbalanced forces. So let's talk about balanced forces. In a balanced force, the net force is 0. That doesn't mean that there's no forces acting on the object. A lot of people get confused about that. All it means is that they all equal out to each other. And for balanced forces, the object could be at rest, like that book sitting on the table, or it could be moving at a constant velocity. So here's one example, a person pushing on a box that's not moving. So what that means, we know that the gravity and the normal force are going to be equal because the box is not falling through the ground. But the reason why this box isn't moving when the person pushes on it, they are applying the same amount of force this direction as friction is applying this direction. So they can't quite overcome that force of friction that is opposing the motion of the box. Draw this in your journal. Now let's look at unbalanced forces. People are a little bit more familiar with unbalanced forces, at least in terms of what the concept means. So for an unbalanced force, the net force obviously is not 0. You're going to have a magnitude of force and it's going to be pointed in some direction. And the object is going to be accelerating in whatever direction that net force is pointed. So for example, we have this roller skater, this roller derby girl here, and she's skating and she's going to be accelerating to the right. So she's not moving at a constant speed, she's getting faster and faster as she goes to the right. A free body diagram for that might look like this. So again, we've got the gravity and the normal force. We have the friction between her skates and the ground, but then notice that the applied force vector is much longer than the friction force vector. That means that she's applying more force in this direction than friction is going the opposite way. And so we can see that this is quite a bit longer and she's going to be accelerating in that direction. That's it for the notes. If you have any questions, be sure to ask. We'll be using these notes on Monday when we do the free body diagram practice.